In this video, we're doing a standard minimization problem, and all I'm going to do is show you how to create the dual. So when we have a minimization problem, and it's a standard minimization problem, the easiest way to solve this problem is to change it into something that we already know how to solve, which is a standard maximization problem. So our objective here is to turn a standard minimization problem into a standard maximization problem and then solve it using the methods that we've already learned. So again, in this video, I'm just going to show you how to do that, change it from a standard min to a standard max problem by creating what we call the dual linear programming problem. All right, first of all, let's verify that this is a standard minimization problem. First of all, it says to minimize, and so again we're using C, and I like to think of C for cost. Cost is something we would minimize. And the objective function has to have all positive terms. So 4s is positive, 5t is positive. Then in the constraints, all the constraints must have greater than or equal to inequality symbols, which they all do. So it is a standard minimization problem. To create the dual, we're going to go back to doing something that we learned how to do in linear algebra, which is to create a matrix. So we're going to create a matrix starting with the first constraint. And so we'll have 8, 3, and 10. Then the second constraint, 9, 2, and 4. The third constraint, 3, 1, and 5. And then we go to the objective function. The objective function is always on the bottom. So we're going to have 4, 5, and a 0 there. So now notice in this particular matrix, if we put matrix symbols around it, this is the S column, the T column, and the constant column. So if we were to call this, let's just say matrix A, to create the dual, we have to find the transpose of this matrix. And so to find the transpose of the matrix, we simply take and interchange the rows and the columns. So I'm going to start with the first row and make it the first column, 8, 3, 10. The second row becomes the second column, 9, 2, 4. The third row becomes the third column, 3, 1, 5. And then the fourth row becomes the fourth column, 4, 5, 0. And this would be the transpose of matrix A. What we want to do now, once we have the transpose, is to go back to an objective function and constraints. Now, I'm going to label this as the X, Y, Z, and constant. So I'm taking the first column, I'm making it my variable X, the second column, my variable Y, third column, my variable C, and the fourth column will be constants. So the objective function is on the bottom. So we're changing this from a standard max into from a standard min into a standard max. So a standard max problem, remember we have P. P equals 10x plus 4y plus 5z. My constraints then, this is going to be subject to, we're going to go to the first row. This would be 8x plus 9y plus 3z is less than or equal to 4. And then 3x plus 2y plus z is less than or equal to 5. Remember, with a standard maximization problem, we have less than or equal to symbols. And so these are my two constraints. So this is the dual. That is what we call the dual. Okay. Couple of notes about this. In the original problem, we started off with two variables, s and t, and we had three constraints. Two variables, three constraints. Two variables, three constraints. But once we create the dual, what happens is we go from two variables, three constraints, we go to three variables and two constraints. They switch. And that will always happen. So, however many variables you have in the original primal problem, that's how many constraints you'll have, and how many constraints you have in the original primal problem, that's how many variables you'll have in the dual problem. One last thing is when you are creating your own problem, I like to have the original problem in terms of like S, R, S, T, U, those variables, because those would be, generally speaking, what we would use for slack variables in a standard maximization problem. And then once we convert it to the dual problem, we use X, Y, and Z. All right, I hope this helped. From this point on, you would basically set this up as a standard maximization problem and solve it.